everyone, and welcome to another Explainer. Today we're jumping right into a really fantastic chemical puzzle. We're going to decode the Reimer Tiemann reaction and look at exactly how precision dictates outcomes in organic chemistry. Think about this for a second. How does changing just one single tiny chemical ingredient completely alter your final product? In organic chemistry, the stakes are incredibly high, right? A chemical recipe demands absolute precision. Swapping out just one seemingly small reagent can completely alter a reaction's destiny. And today, we're exploring that exact phenomenon. So just to make sure we're all on the same page, let's quickly define the foundational concept we're looking at today. The Reimer Tiemann reaction is a process where phenols react with specific reagents in an aqueous alkali. They're heated to exactly 340 Kelvin, followed by hydrolysis, and that forms distinct aromatic compounds. I know, it sounds like a lot, but don't worry, we're going to unpack every single piece of this step by step. Okay, let's dive into this. If you look at the setup here, we basically have what looks like two parallel tracks mirroring each other. It's this beautifully organized dual pathway. We've got a top equation and a bottom equation. And sure, they look almost identical at first glance, but as we trace the reaction of these phenols from left to right, we're going to discover a really brilliant fork in the road. Section 1. Base ingredients, the constant conditions. So think of this like the base of a recipe. Whether you're looking at the top equation or the bottom equation, a few core elements are absolutely constant. First, the starting reactant is always phenol. You know, that classic hexagonal benzene ring with an OH group attached. Second, the reaction always takes place in an aqueous alkali medium, specifically sodium hydroxide, or NaOH. Third, the temperature is strictly locked in at 340 Kelvin. And finally, the whole process is followed by hydrolysis. These are essentially your non-negotiables. Section 2, Pathway 1, the chloroform route. Now here is where pathways diverge. Into those stable baseline conditions we just talked about, we're going to introduce our very first variable ingredient, chloroform. Chemically, that's CHCl3. And this one choice of reagent is what dictates literally everything that happens next. Let's break down that top equation chronologically to really see the mechanism here. Step 1, our phenol reacts with the chloroform, the CHCl3. Step 2, notice that exactly 3 units of our aqueous alkali, NaOH, are added, and the heat is applied at 340 K. Then, step 3 is the big reveal. The resulting primary product is salicylaldehyde. You can see the ring now features a brand new CHO group attached right next to the OH, and alongside it, as byproducts, we get 3 units of NaCl and 2 units of water. Section 3, Pathway 2, the carbon tetrachloride pivot. Okay, let's reset the board. We've still got our phenol, our aqueous alkali, and our 340 Kelvin temperature. But this time, at the exact moment we would have added chloroform, we swap it out for carbon tetrachloride, CCl4. We literally just traded a hydrogen atom for 1 extra chlorine atom in our starting reagent. And as you'll see, that fundamentally alters the reaction's entire destiny. Outlining this bottom pathway step by step, the contrast is super clear. Step 1, phenol reacts with the CCl4. Step 2, notice the subtle shift here. We now actually need 4 units of NaOH instead of 3, still at that 340 K. And step 3 reveals a completely new final product, salicylic acid. Instead of the CHO group from before, we now have a COOH group attached to the phenol ring. It is a totally different chemical identity, all because of that initial swap. Plus, we get 4 units of NaCl and 2 units of H2O. Section 4. Comparing the final products. Putting them side by side really highlights the core rule here. It's a wonderfully strict input-output relationship. If your input reagent is chloroform, your output is going to be an aldehyde, specifically salicylaldehyde. But if your input reagent is carbon tetrachloride, your output is an acid, salicylic acid. It's just so predictably binary. Now, what's really interesting about this slide is the subtle math playing out in the background, because it isn't just the primary product that changes, right? The supporting chemistry actually has to balance itself out to accommodate that new reagent. Let's look at the actual stoichiometric numbers. In the top reaction with CHCl3, we needed 3 units of NaOH, and we produced 3 units of NaCl. But look at the bottom reaction with CCl4. Because we brought in an extra chlorine atom right at the beginning, carbon tetrachloride has 4 chlorines compared to chloroform's 3, the math has to adjust. The reaction demands an extra unit of our base, meaning 4 units of NaOH, and in turn it produces an extra unit of salt, yielding 4 units of NaCl. Interestingly though, the water output, 2 units of H2O, stays exactly the same across both. And you can see this elegance perfectly reflected in the visual evidence we have. Just let your eyes trace the balancing numbers. Look at the 3s scattered across the top row, 3 NaOH, 3 NaCl. Then drop down to the bottom row and you see the 4s taking their place, 4 NaOH, 4 NaCl. The chemistry is literally forcing the mathematical necessity right in front of us. The source text actually summarizes this entire phenomenon perfectly with one incredibly clear statement. When CCl4 is taken instead of CHCl3, salicylic acid is formed. Honestly, that one sentence is the ultimate thesis statement for this entire Reimer Tiemann matrix we've just mapped out. So we've seen how precise and honestly unforgiving this chemical fork in the road is. A simple swap from chloroform to carbon tetrachloride completely changes an aldehyde into an acid. But I want to leave you with a thought before we wrap up today. What real-world applications rely on controlling this precise chemical fork? Think about it. When industrial chemists need salicylic acid versus salicylaldehyde for, say, medications or fragrances or new materials, this exact equation is the blueprint they have to follow. Thanks for joining me for this explainer, guys, and keep questioning.